we did the example 5.5, and a was given to us as the initial value. And it turns out that one was a little simpler than the ones that are in your homework, because the initial values for your 21 and 24, they're talking like end of day initial values. So I wish they would have been a little bit more clear in the instructions about this. Because with 23, it says the initial value is 10. It gives you the limit to growth, all of that good stuff. And we know we have this model right here. And this requires an extra step. That extra step is, what is A? Because they're not using the initial value of 10 as A. It's kind of like a, what was in our problem? One of the problems that we did said, at the end of the day, it's this. And so that's kind of how they're thinking here. So with these, you have to do a little bit more math. And you have to say, all right, if my initial value is 10, that means it came out to 10 right here. I know my limit to growth was 40, and I'll have 1 plus A, because I don't know what that is yet. But I do know that that's supposed to be at time 0. So I should have my base to 0, and I don't even need to worry about finding the base until after I know what A is. So then what we do is say, well, anything with 0 power is 1. So this will be 10 equals 40 over 1 plus A. I can do my cross multiplying. Then I'll divide and subtract. And it turns out the initial value for this one is actually 3. And looking back at that example, we're going to need to change it because our example, whether or not you do this or not, it stays 5. But with the book problems that you have in your homework, it can actually, your A value can actually change based on what they have for that initial value. So a little bit more work. Like I said, it's now you have A. Now you can do the math that matched everything that we did in class. But it's a little bit tougher than the problem that we did in class. And that's not really fair. So we'll have to beef up that example for the next few years. Anything else we should talk about for the homework? So whatever you have done that has your name on it, go ahead and pass that up. I would love to take that from you. It says logarithmic functions and their graphs. Today is just going to be about logarithmic functions. We're not going to focus on any graphing until tomorrow. We will be able to use inverses of exponential functions. Those are logarithms. We've already been doing that. So a lot of this should feel like, in fact, today, resist the urge to overthink. We have already done things that are more difficult than what we're going to see here today. So resist the urge to overthink. Use common logarithms. That's common logarithm is base 10. And that is the one on your calculator that just says LOG. And it doesn't have a base on it. And that's because when it's not there, we are supposed to assume that it's a 10. Just like when you say X, you really mean 1X, but the 1 is not there. Then natural logarithms, that's our logarithm base E, Ln, and that's the same thing as logarithm base E. Graph logarithmic functions, that's tomorrow. Answer questions about measuring sound in decibels, that's tomorrow. So today, just some real basic things having to do with logarithms that we might have forgotten since last year. I mean, logarithms, sometimes we forget things that are super easy. And logarithms are a really quick chapter in Algebra 2 because it's very basic. And so we tend to forget that stuff, but this will bring it back for us. We revisited the horizontal line test in section 1.4. What did we use it for? Okay, so the vertical line test was to show whether or not something was a function. What was the horizontal line test for? If its inverse is a function. So to test if the inverse of a function is a function. So we've got exponential growth and exponential decay right here. Here's the growth, here's the decay. And if we draw a horizontal line anywhere on these graphs, it will only touch them in one spot, which means their inverses are functions. So their inverse is what we're interested in today. And it's what we've been using as we've been solving some of our logistic functions from the last section. So down here, it says for the exponential function f of x equals b to the x, the inverse is the logarithmic function with base b. Okay, that's a lot of blah, blah, blah. We have that. We want to get rid of it. Well, when you have unknown powers, you use logarithms to get rid of them, and you have to make the bases match. So logarithm base b would make all of that drop out, and we would get x. So that's why it works. Logarithm base b of x. We have to have the bases match. That's how we undo exponential functions is what they're called, but it's unknown exponents is really what we're after. That's what we're trying to find. So, bit of history. Logarithmic functions were developed around 1594, long time ago, as computational tools by Scottish mathematician John Napier. And there are some tools out there that he was involved with called Napier's tools, involved in like machining and that kind of stuff. And he was around from 1550 to 1617. He originally called them artificial numbers. Caused a problem. Later on people started working with imaginary numbers and they're like, okay, imaginary, artificial, there's going to be some problems here. And so he decided to they changed that name to logarithms, which means reckoning numbers. Reckoning means to check. So these are the numbers that are used to check exponential situations, exponential functions. Now we do want to remember as we get to the graphing tomorrow that inverses are always a visual reflection over the line y equals x, that line 1, 1, 2, 2, 3, 3. So if we have exponential growth and we reflect that over the line y equals x, that's where we get our logarithmic functions. But like I said, the graphing we're going to focus more on tomorrow. Today is really about the first parts of our objective here, which is using common logarithms, using natural logarithms, getting back into the habit of using logarithms. If f of x equals b to the x, where the base is greater than 0, and b is not 1, because 1 to any power is just 1, there's nothing fun about that, then the inverse of f of x is going to be the logarithm base b of x. Got to make the bases match. That's what we have to do. So changing between logarithmic and exponential form. And again, they say if x is greater than 0, so we have a number we're trying to evaluate that's going to be positive. And b is greater than 0, reading that backwards. So our b value, our base, is going to be positive. And it's not equal to 1, because again, 1 to any power is just 1. Y equals logarithm base b of x if and only if. Well, let's see here. Logarithm base b of x equals y. Logarithms are kind of hard for us to understand, and that's mostly because you were just introduced to them last year. So what you have to do with logarithms is you have to translate them, just like any language. You learn a few words, and in your head you're thinking, oh yeah, that's the same as. And to translate it, what we do is we make a snail shell. A snail shell looks like this. That's the snail shell. So what we want to do is translate logarithm base b of x equals y into something we've been studying already, which would be exponential functions. To do that, we start with the base and we make a snail shell. B to the y equals x. So that's what that logarithm statement really says in exponential form. Logarithms have two forms. They have their logarithmic form and then they have an exponential form. And usually it's the exponential form that we think in because it's like our first language. We learn English. The first language we learned was exponents. Then logarithms came later, so we translate that. And that's how we get the exponential form. B to the y equals x. So, nice little snail shell. Get that come up there. That linking statement says that a logarithm is an exponent. So what that tells us is logarithms and exponents are in the same classification, and that means what we have to do is think, so the rules that work for exponents also work for logarithms. They have to, because if we're going to use them as inverses, they have to follow the same rules. Because logarithms are exponents, we can evaluate simple logarithmic expressions using our understanding of exponents. So using the properties of exponents, which we've been talking a little bit about, not a whole lot. Things like when you want to multiply similar bases, you have to add the exponents. So with logarithms, if we want to multiply logarithms, we're actually going to have to add because they follow the same rule as exponents. If we have logarithms where they ask us to divide, we think, okay, if I had the same base, if I had x to the fifth divided by x to the third, well, yeah, I'm supposed to subtract. So division will be subtraction. If we're supposed to raise a power to a power, x to the third raised to the seventh power, well, that's multiplication. So if we have logarithms that are going to need to be raising powers, we're going to have to multiply to make that happen. We're not going to do a lot of that kind of thing today. Today is just about the basics, but we're definitely going to get into using logarithms a little bit more. So this says evaluating logarithms. And at first, when you learned this, logarithm base 2 of 8 equals 3, you went, what on earth is that trying to say? But when you learn to snail shell this in your head, it says 2 to the third equals 8. Well, that makes perfect sense. That's 2 times 2 times 2 equals 8. Of course, it works. For B, this will say 3 to the 1/2 equals the square root of 3. And again, you say, of course it does. 1/2 power square root makes perfect sense. 5 to the -2 equals 1/25. Now that might take a second. You might have to think in 2 steps here. Negative makes it a reciprocal. Yep, so it'd be 1 over 5. And then I'd have to square it. So yeah, it'd be 1 over 25. Makes sense. Got it. 4 to the 0 equals 1. Of course it does. Anything to the 0 power is 1. And this last one says 7 to the first equals 7. Or you notice, hey, these bases match. Those are total inverses of each other. That's going to be 1. And you go that way. So 2 different ways to get what we need out of our logarithms there. And again, just some basic, hey, this is how we translate what we see in logarithms into exponential language. So now we have some extra examples. And the key to this is going to be thinking snail shell. Now I've got to get this into a language I can understand. So this one would say 3 to the x equals 27. So what would x have to be? Have to be 3. 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. So x is 3. So we snail shell it. Think through the process. This one you'd have to snail shell from the left, which I'm not the best at because I'm right-handed. So 4 to the x equals 1 over 64. Okay, wait a minute. How did that become a fraction? Had to be a negative. Had to be. And then 4 to the something is 64. What's the something? 3. So this is going to be -3. So when you see a fraction, it's kind of 2-step thinking. Okay, how do I get a fraction? Now how do I get 4 to be 64? Because the negative power makes that happen. Now this one's going to be a little different. 2 to the x pardon me, equals the square root of 32. This one requires steps in it. The first thing would be, I'm dealing with powers and they throw me a square root. I better change that. I'll make that 32 to the 1/2. And then we use a process called equalizing bases. So I start to think, 32, is it 2 to the something? 2 to the what? 5th. So this is really 2 to the x equals 2 to the 5th raised to the 1/2. And here's where I use one of those properties of powers and say, when you raise a power to a power, you're supposed to multiply. So that's like 5 over 1 times 1 over 2. Top times top, bottom times bottom. That's going to be 5/2. So my answer has to be 5/2. And And there it is. So a few more steps with that. And there's more to think through. This first one for A, definitely a one-step problem. Some of you probably didn't even have to write down the 3 that x equals 27. You just did that in your head. B, definitely a two-step. We need a negative to make it a fraction, and then how do we get 4 to be 64? But with C, there's a little bit more to that. A little bit more of writing down steps to be able to get there. So now some basics of logarithms. Basic properties of logarithms, again, our base is going to be greater than 0. Our bases will be positive, not going to be 1, because 1 to any power is just 1, which is boring. And our x value is going to be greater than 0 for any real number y. Logarithm base b of 1 is always 0, because if you snail shell it, it's going to say b to the 0 equals something. And anything to the 0 power is going to be 1. Logarithm base b of b equals 1, because if we snail shell it, it says b to the first equals b, which of course it does. Down here, logarithm base b of b to the y equals y. Well, if you snail shell, you get b to the y equals b to the y. But the first thing I noticed here was these bases match. Those are inverses. They're going to be gone. Those bases match. We have our unknown base being raised to a logarithm power in this one. These two bases match. Boom. Answer's x. That's off the slide. So you can snail shell those, but probably a better plan to get used to, okay, let's check these bases out. Let's see if the bases are the same, because then they're going to drop out. Using these properties, use equal bases to evaluate the logarithmic and exponential expressions in example 2. All right, well, let's do that. So, if we don't know something in math and algebra, we make it an unknown. And if you're thinking, well, how am I going to snail shell that because there's nothing on the other side, then just make it an x and snail shell it so that you can think through it. That's not a pretty looking problem. What power would you raise 5 to get B125? 3. So there's our answer right there. Next one, same type of thing where you say, okay, let me throw an x over there. 5 to the x equals the square root of 5. Bad plan. We're supposed to be talking powers. Square root of 5 is what? Is a power. Half. So 5 to the x equals 5 to the 1/2. Well, x has to equal 1/2. Has to. The only way that's going to work. C is supposed to be a little more basic than that. What do you notice about C? Got the inverses. 2 bases of 6, boom, they're gone. Answer's 11. And there it is. So, watching for those bases, do my bases match. And I'm going to pull out the duckies today. So, I'll give you a second. Well, not a second. I'll give you more than a second. But these are supposed to be basic. So, go through. Snail shell them. At this point, when we're just trying to get your memory back here, good thing to do. Excellent. You're talking to each other. Do that. Before I start pulling duckies, then you'll feel comfortable when I call you here. Check in with somebody. Elbow partner. right, let's come together now and see what everybody was getting. So the first one up there says we're going to evaluate the following logarithm base 5 of 1. Ashley, what'd you get for that one? Five of the 0 equals 1. Well, the next one looks harder. It has a fraction base. Log base 1/2 of 1. So, Ava. Yeah. Still 0. Doesn't matter what that base is if we're saying that it has to come out to be 1 when we snail shell it. So that means Madison, C is also 0. Doesn't matter what the base is. All right, then D. Yeah, what'd you get for D? 1. 12 to the something is 12. There it is. For E, Andrew. 1. Something is B. Now F and G, I heard a few people talking about this. So Tommy, what'd you do for F? I got 1. That's exactly what it is. Ln is logarithm base E. And sometimes it helps to just write it down that way. So you see, oh, logarithm base E of E. Hey, that's going to be 1. Claire, so what's G? 1. Logarithm base 10 of 10. 1. So there it is. So what we're doing again is we're trying to get to these objectives, and this is a piece of it, because we're trying to understand the logarithm base E and the logarithm base 10 a little bit better. And sometimes it helps to write it out. Okay, it's just LOG. It should be LOG base 10. That's how I want to think of it. Ln, I want to write that as logarithm base E and go through it that way. So we have these tables. What is this table business all about? Logarithmic functions are inverse of exponential functions. Of course they are. We've been using them to solve our logistic functions that way. So the inputs and the outputs are switched. For every inverse, that happens. The x's become the y's. So if we have the graph of 2 to the x, here's our x's, here's what we get for y's, then the logarithm base 2 should be the reverse of that. The x's and y's should switch. And that's what happens. This goes here, and this goes here. And they switch positions. So some books will teach you to look at the base of your logarithm when you want to graph, and just think, what would this look like exponentially, and go with it that way. We're going to kind of use that when we talk about our graphing tomorrow. But we do want to remember that they're inverses of each other when we go through. So common logarithms are our base 10 logarithms. And like I said, they're called common logarithms. That's what they are. And that's because our number system is base 10. So because of their connection to our base 10 number system, the metric system, and scientific notation, common logarithms are especially useful. That's why they're on our calculator. You don't see base 2 logarithms on our calculator. LOG 10, very common, a lot of uses for them. And then also LN, logarithm base E, because we have a lot of uses for those as well. So the common logarithmic function, logarithm base 10 of x, we are just going to see on the calculator, any calculator, as LOGX. It's assumed that we know that that's going to be a base of 10. So that's the inverse of the exponential function, f of x equals 10 to the x. Well, of course it is. The bases have to match. So that's what's going to happen. And y equals the logarithm of x, if and only if, well, we have to be able to snail shell here, so there's a little 10. 10 to the y equals x. There it is. So we can still think in terms of exponents. Make it exponential so that we can say to ourselves, all right, now I can understand this. This is making sense. I can snail shell and things will go well. Basic properties of common logarithms, we just found out. It doesn't matter what the base is. If this says 1, this is a 0, because any base to the 0 power is going to give us 1. Logarithm base 10 of 10, well, you put that little 10 there, it's pretty obvious the base is matched. logarithm base 10 of 10 to the y. Well, the 10s are going to cancel out. Log 10 of 10. And the y will be left. And down here, we have 10 logarithm, and it just says of x, but remember there's a little imaginary 10 there. So those two bases match again, and boom, they're done. And you get x. Well, that's how it works. So down here, it says we want to evaluate logarithmic and exponential expressions. So we've got some to look at. And this is just LOG. So the first thing I do is I think, okay, that's base 10. Get that through to my head there. That is base 10. And I don't know what it is, so I'm going to put an X there. But I bet even before I put that down, everybody knew what the answer to this one was. What is it? 10 to the something is 100. That something is 2. So over here we do the same type of thing. Think our way through this. 10 to the something is the 5th root of 10. Well, 5th root isn't going to help me. I need to see a power. What's 5th root as a power? 1/5. Well then, by golly, x equals 1/5. So sometimes writing a couple of extra little steps down makes it click. Ooh, C looks tough. All right, let's see what we can do with that one. Base 10 equals x. So 10 to the x equals 1/1000. What did they do with that power to get us a fraction? They have a negative. What power do you raise 10 to get 1,000? There it is. D. Trick question. What is it? 6. There it is. So looking for those inverses. Bases that match. Extra examples? Go after those. I'll call out your duckies. No, I pulled your duck. What's A doing? That's exactly what it's doing. Inverses right there. So we're left with 3x squared plus 2. B usually makes people squirm for a second, but then they figure out, oh, I'm overthinking it. Here today. Tyler. C, Elena S. It is 5x. And this is one people tend to overthink because they're like, okay, which 5 do I cross out? It actually doesn't make any difference which set of 5s you cross out. And most people will do that one. Joey, you got D. That's X. E to the logarithm base E of X. Inverses. E, Carter. X. And F, Lydia. X. You're all thinking, what is our homework going to look like today? Well, remember to look for the inverses. All right, down here, warning. The calculator. I mean, that's the warning. Back when we chased dinosaurs for fun in our spare times, we didn't have calculators. So our math books actually had about 100 pages filled with logarithms. In fact, the book, and we had to flip to the back and look them up. You guys don't have to do that. You have a beautiful little memory chip in your calculator that pops those out for you. So when checking with your calculator, make sure you use the answer key. Otherwise, you're going to have rounding errors. It just absolutely happens with logarithms. The other thing that we need to do is, in here, we do just about everything to 3 decimal places. Logarithms are one of the things that we do in 4. So with logarithms, because historically people have always gone to the 10,000s position, we're going to use 4 decimal places for logarithms. So if we use the answer key, sometimes even when we use the answer key, the graphic calculator will make a mistake. It just does that. So here's what they're saying we should do. And you guys can punch this along in with me. If we're asked to find the logarithm of 34.5, so log 34.5, and we get our answer. And we decide that just seems really weird. You know what? I'm going to check that. So if it says log, it really means log base 10. And if I snail shell this, it'll say 10 to the x equals 34.5. So that means what I just got there is the power I should raise 10 to. All right, so 10 to the second negative, so it's pulling up the answer I just pressed in, should give me 34.5 right back. And it does. But if we stopped and rounded to 4 decimal places, came over here and said, okay, 1.5378. We're not going to get a perfect 34.5. We're just not. 10 to the 1.5378. It's close, but it's not exact. So important, especially when we're checking our answers, that we are using that little second negative button on our calculator. So we're pulling up all the decimals that come with it. And like I said, occasionally, even when you do that, you'll see, wait a minute, this didn't give me the exact answer right back. And it's just because the calculator has only so much space. So it's doing what it can do. So now in example 4, this is just basically, can you punch stuff in and know that you need to go to 4 decimal places is what we're doing here. So use a calculator to evaluate the logarithmic expression if it is defined. Ooh. Interesting. And check your result by evaluating the corresponding exponential expression. Oh, we just did this one. 34.5, 1.5378. And again, we know that to check it, we'd snail shell 10 to the and use the whole line up there, not necessarily just the 1.5378. And then we need to punch in log of 0.43. And negative 0.3665. So again, if we wanted to check that, we'd say 10 to the answer I just got. Hey, that's 0.43. It works. And then log negative 3. Oh, non-real answer. Quit. Go to. So I'm going to quit out of that. So they're trying to tell me, oh, stop and think for a second what your calculator's talking to you. Stop and think for a second. You know you can't do this. 10 to the something equals negative 3. How are you going to pull that off? Well, you can't in a real number system. So in the real number system, this is undefined. Now, if you set your calculator to complex numbers, it's going to try and give you an imaginary number that will work with this. But when you check it, it won't take it back. So it's best for us to just stick in the real number system anyway, because we're talking about real answers, application answers. Don't write all of this down. It's just explaining what I just said, which is the log of negative 3 is undefined. Because there isn't any real number, 10 to the something equals negative 3. It is not going to happen. A graphing calculator will yield either an error message like we had or a complex number answered for entries such as log of negative 3. But we're going to restrict our domain of the logarithmic functions to the set of positive real numbers anyway, since we are talking about application problems. So ignore complex number answers. Solving simple logarithmic equations. Well, that sounds nice. Solve each equation by changing it to exponential form. So the fancy name for snail shelling is exponentiated. That's what it is. So when they say change it to exponential form, they want us to put a little 10 there and say 10 to the third equals x, bless you. And then what is 10 to the third? 1,000. So there's our answer. Hey, that was a simple logarithmic equation. Let's try B. When you snail shell that, what's it going to look like? 2 to the 5th equals x. we've seen 2 to the 5th a couple of times today. What is 2 to the 5th? 2 to the 5th is 32. And there it is. Now we've got some extra examples down here. And it doesn't say these are simple ones, so some of them might be a little tougher. But if there's no base there and it says log, what is the base? 10. 10 squared equals z. Oh, that's 100. B looks like it has a little more meat to it. Let's do that one. 2 to the 4th equals z plus 1. Oh, that's 2 to the 4th. 16. Well, this isn't the hardest problem we've ever done. Just subtract 1 from both sides and we have 15. Hey, maybe C is harder. It has a fraction base. Maybe that's supposed to be hard. Let's see. So 1/2 to the 5th. Oops. Better make some space. Equals 2z plus 3. So can we distribute the 5? Yeah, because there's pure division. Pure multiplication and division in parentheses we can distribute. So 1 to the 5th is 1, 2 to the 5th is 32. Hey, that's no problem. But now we have to subtract 3 from both sides. So we better figure out how many 30 seconds 3 is. So 32 times 3 is 96. We need to subtract 96 30 seconds. That's not going to be pleasant. Negative 95 30 seconds. Equals 2z. Oh, you're the 2. Multiply by 1/2. Yeah, you could say, hey, I'm going to divide by 2, but with you already have a fraction on the other side. Multiply by 1/2 means we're just going to double that denominator. So we get negative 95 64ths for z. Checkable. We can put it back up there. Make sure it works. D looks a little easier. Z squared equals 25. Hey, if we had that problem in our Algebra 2 book, we'd take the square root of both sides, and we would say z equals plus or minus 5. We're not in Algebra 2. We're doing word problems. If we're doing word problems, what are we going to use? Just the 5. Just the positive 5. Right there. Well, maybe E is a little more challenging. You have to snail shell the left here. 5 to the z equals 5/25. Or 5/125. Hey, that's not even reduced. They must be trying to pull a fast one. What does 5/125 reduce to? How many quarters in $1.25? 5. So what, oops, so I wrote a 5 instead of 25. Power here, what would you need? Yep, gotta have the negative to get the 1 on the top, a 2, make that 5 to 25. Oh yeah, I make a line through my Z's because I don't want them to look like 2's. Which apparently they did anyway. So, next up, natural logarithm base E. Let me here. Natural logarithm base E is ln. And that's just logarithm base E. Because of their special calculus properties, logarithms with base E are used in many situations. Logarithms with the natural base E are natural logarithms, and that's ln. So y equals ln x. Ooh, we better snail shell that and see what that says. So logarithm base E of x equals y. That says e to the y equals x. Yep, that's what it says. Have to do the little snail shell there. Now, it doesn't matter that this is base E versus any other base. The basic properties of natural logarithms are the same as the properties that we saw for our other logarithms. You just have to think, hey, base is E. E to the something is 1. Has to be 0. Has to be. natural log E, you have to think, well, that's logarithm base E. Hey, those are inverses of each other. Those are going to cancel right out. Same thing here, inverses of each other. Going to cancel right out. And you certainly could write logarithm base E, and then you could snail shell, and it's going to make perfect sense. But just because we suddenly switch to logarithm base E doesn't mean that things get lots harder. So take a look at and go ahead and write down your answers for A, B, and C. And then I'll call out the duckies. Again, don't overthink. So the first ducky actually gets the hardest problem of these three. Because out of all of these, A is probably the most difficult. Alyssa, I pulled your ducky. And that's what you should get. So you rewrite it as logarithm base E, E to the 1/2, because we want to see it as powers. These are going to cancel. Boom, inverses, right there. B, Will, what's the answer to B? 5. It's 5. These are inverses. Annie, how about C? 4. Pretty basic. We need to know that ln is logarithm base E. Going to drop right out. And then evaluating natural logs with the calculator. We've already been doing this when we were solving our logistics. So just make sure we go 4 decimal places. ln 23.5. Oh, and finish off the parentheses. These calculators don't care. It's just kind of nice to see it all perfect there. So 3.1570. Again, if you wanted to check it, you'd do second ln e to the x of the answer. Well, 23.5. So yeah, we'll start here tomorrow. I mean, we already, watching you guys, I know you probably already have those next 2 written down already anyway. But we're working towards our objectives here. And yeah, it's not going to take me very long to do 1 to 36 after seeing what we did today. Oh my goodness, what a huge assignment! Well, not when you think about what we would have done. So, there it is.